Hello, I welcome you all in this course on power plant engineering, and today we will discuss the direct energy conversion. The direct energy conversion means the conversion of available energy into the electricity by not having any intermediate stage of energy. For example, when we develop energy using Rankine cycle, so what we do, we available energy is coal, or we burn the coal, heat is generated, and that heat is converted into the useful work by using Rankine cycle. Output of Rankine cycle is coupled with the generator and electricity is generated. So, this is a conventional type of or indirect type of energy conversion of energy in the coal to the electricity. So, it is passing through various stages. In direct energy conversion, the available energy is directly converted to electricity. For example, photovoltaic cell, it is the best example of direct energy conversion. The moment the sun rays fall, the available energy may be very thin, it does not matter. So, when the rays of the sun are falling on the this photovoltaic cell, immediately the due to photovoltaic effect, the energy is converted to the electricity, or we get the electrical output. So, these type of conversion, there are other methods also for converting direct energy from source to the electricity. We will discuss them one by one. So, in those, I mean, photovoltaic we have already discussed. In addition to that, it is thermoelectric conversion system, which is known as the direct energy conversion system, thermionic conversion system, MHD, magneto-hydrodynamic system, electrostatic mechanical generator, though it generates very small amount of energy, but it is also direct energy conversion, electro gas dynamic generator, EGD, and nuclear batteries. So, we will start with the thermoelectric conversion system, thermoelectric. As it implies from the name itself, thermoelectric means heat into the electricity. Now, there are three effects. One is Seebeck effect, another is Peltier effect, and the third one is Thomson effect. Now, Seebeck effect says if there is a junction of dissimilar materials, right, and these junctions are kept at different temperatures, EMF will be generated, right. So, this is Seebeck effect. Peltier effect is reverse of the Seebeck effect. If you have junction of different materials and the current is passed, either junction will become hot or it will become cold. So, if you have junction of any two materials A and B, and if you pass the current, so either it will become hot or it will become cold. So, this effect is used in thermoelectric refrigeration systems. So, we have a junction. So, when the electricity is passed through the junction, it becomes cold. So, that is known as thermoelectric refrigeration system. But here our requirement is different. Here our requirement is we want to convert heat into the EMF. So, for this we will go for the Seebeck effect, right. So, the junctions will be kept at different temperature and we will generate the EMF. So, this is a sort of direct energy conversion. There is a Thomson effect also. Suppose there is no junction, there is a wire of the same material and there is a temperature difference between these two ends. EMF will also generated along the wire as well. So, here for our concern is only Seebeck effect. Now, for Seebeck effect, we have to choose the material. When we choose the material, we should know its mechanical characteristics, stability. The material should remain stable and material should be mechanically sound. Under operating condition, it should remain stable, and under fabrication also it should remain stable. In both the cases, it should remain stable. So, for this bismuth telluride is considered to be the best suited. So, bismuth telluride has enormous application as far as thermoelectric conversion of or direct energy conversion is required. So, this appears to be the most suitable material if we consider all these constraints. Second thing is for the bismuth tellurium is that it can produce alloy with bismuth, selenide, antimony, telluride, lead, selenide, and tin. So it can make the alloys also, and the properties of alloy, thermoelectric properties of alloy, thermoelectric properties of this bismuth telluride can further be improved by making alloys, right. Thermoelectricity can also be produced. There is an option by taking heat from the nuclear core. The nuclear, if you go for the nuclear power plant, the core temperature is very high. So if you take core as a hot junction, room as a cold junction, there also you can generate the EMF. Nowadays, research is also going on to generate this mobile charger with the help of stoves. So stove surface can be hot junction, room can be a cold junction, EMF can be generated, and then EMF can, with the help of this, we can develop a mobile charger can be developed. So in those areas where electricity is not there, people can further use the mobile. So there are several applications for thermoelectric conversion. So there is a factor figure of merit Z. So for any, we cannot go for any alloy or any material. So Z has to be seen. We have to look into the Z. For example, lead telluride, sorry, lead PB, lead telluride. The value of Z is Z into 10 to power 3 is equal to 1.5 lead telluride. For bismuth telluride, it is equal to 4. For germanium telluride is equal to 1.5. For many compounds or the alloys it is given, compounds and alloys it is given, and we have to go for the best value of Z. That is the one of the criteria of choosing a material for thermoelectric purpose. Now Z is, figure of merit is S square divided by rho K. S is Seebeck coefficient, so it differs from material to material. Rho is specific resistance. Specific resistance is expressed in terms of ohm meter. And K is nothing but thermal conductivity, right. From this we get the value of Z, and the alloy or the compound which is giving the best value of Z should be used for thermoelectric refrigeration system. Sorry, thermoelectric energy generation. Now, how to achieve high efficiency? This is always a concern for any machine, to achieve high efficiency. In order to achieve high efficiency, as I said, Z is equal to S square by rho K. We have to have high value of Z. So, thermal conductivity has to be low. Specific resistance that is rho, this K, this is rho has to be low. Specific electrical resistance. Specific electrical resistance has to be low, thermal conductivity has to be low, and Seebeck coefficient has to be high. Mobility of the current carrier, it should be high. Mobility of the current carrier should be high, and second thing is, for high efficiency, the material should not crack. The material which is used for this purpose should not crack while manufacturing, while use, and it should resist oxidation, because at high temperature there is a possibility that the metal will get oxidized. So, it should resist the oxidation, it should have good material strength, and it should be amply elastic. So, these are the requirement for thermoelectric conversion system, which can convert heat into the directly heat into the current. Next is thermionic system. This is conversion system. Thermionic conversion system. It means we are heating a plate. Simply when you are heating a plate at high temperature, the electrons will be emitted, right? Especially when you do it in the vacuum. When you do it in the vacuum, the electrons will be emitted. And you must have heard about the cathode ray experiment where there was a tube, right? This side plate was heated and this is cathode. Actually, this experiment was done not to, so this experiment was not conducted to find, the nuclear structure, though this experiment has a significant contribution in establishing the structure of an atom. This experiment was conducted to simply to find the conductivity of gases under low pressure. So, when this experiment was conducted, the tube was put under vacuum, close to the perfect vacuum. This side was heated. Then a phenomena was seen, there was a sudden glow on this side and the electrons moved from this plate to this plate and the current was flown. So, that is how the electrons were discovered, and on the similar principle, the electricity is also generated in thermionic systems. The plate is heated under vacuum. So, in a thermionic system, suppose we take a cylinder and there is a plate. This is an evacuated tube and this is cathode, and cathode has coolant also, because in due course of time this will get heated, or is known as cold electrode, right, and this is hot electrode. So, in fact, this is a cathode and this side is anode, and this under vacuum, this cathode is heated and electrons are liberated from the surface. There is a term which is known as work function, phi. It is the amount of energy which is required to bring the electrons just at the stage of releasing from the surface, or they are brought to the surface, the work required to bring the electrons to the surface, zero energy level. Any addition of energy will liberate the electrons. So, this is known as work function, because the metals have free electrons. So, when these free electrons are excited by energy, energy can be thermal energy also, they leave the metal, right. So, for this phenomena or this concept of work function has come into the picture. It is expressed in terms of electron volts, and it depends upon the nature of material, of metal and surface finish, right. For example, you take cesium. If you take cesium and cesium is heated up to 1000 degrees centigrade. So, in this case 10% of energy can be converted into the electricity. If you go for the higher temperature, 40% thermal energy can be converted into the electrical energy, right. So, let us go back to this construction. So, from here the electrons flow to the DC load, and from DC load to this. So, current flows in this direction, in opposite direction, because electrons will be coming here and entering here, right. This is cold junction, hot junction, cathode and anode, rest. So, this part when is heated, when heat input is given, electrons are liberated, because vacuum is there, they immediately travel to the anode. So, the circuit is completed. Now, so the anode should have a low work function. It should be like, so that's why barium or strontium is used for this purpose. Cathode should have high, so tungsten is used for this. Tungsten is used for this. So if we go temperature around 2000 degrees centigrade, as I said earlier in this case of cesium, in other material also, the efficiency is approximately 35%. Now this system can make use of any fuel because we need heat only. So how heat is generated, we are not concerned. So any type of fossil fuel can be used, right? And this electric output is of the order of, I mean, it is few watts. I mean, if you were to say the density is approximately, let us say, typical density is 6 watts per meter square. It can go up to 13 watts per meter square. The energy density is of this order in this case. Now, for emitter, now properties of emitter which emits the electrons. So, emitter should have sufficient electrons, free electrons, right, and it should have low rate of deterioration because it will be put under the heat. So, the low rate of deterioration has to be there for the emitter. Emissivity has to be low for emitter. Emissivity has to be low. So, heat is not lost through by radiation from the emitter. Second thing is, because when we heat emitter to a temperature up to 2000 degrees centigrade, some part of the emitter may get also vaporized. So, this metal vapor should not deposit on anode. The metal vapor which is generated at cathode, because cathode is a very high temperature, maybe at 2000 degrees centigrade. So, some part of the cathode may get vaporized. So, it should not deposit on anode, otherwise it will efficiency of the system will go down. So, these are the required property of an emitter in a thermionic system. Now, let us come to the MHD. MHD is known as magneto hydrodynamic system, MHD, and it works on the Faraday's principle, and it is clear from the name itself, right. The electromagnetic effect is used. The principle of electromagnetic effect is also used here. So, if there is a conductor, and there is a perpendicular electric field. It is a conductor is crossing the magnetic field, and it is moving with a certain velocity. EMF will be generated across the edge of the conductor, right. And this principle is also used in many of the applications. For example, your ceiling fan. In ceiling fan, there is a conductor, there is a magnet, electromagnet, and when the conductor rotates, it does the rotational motion, not the linear motion. When the rotational motion is done, then it is reverse of this. When EMF is applied in electromagnetic field, rotational motion results in a fan. So, it works on the reverse principle of this. Another is when a conductor moves in a like electricity generator, electric power generator. In electric power generator, the armature which rotates in a magnetic field, electromagnetic field, and that is how the voltage across the armature is developed, and we get the output from the motor, right. So, here also because it is magneto-hydrodynamic system, here ionized gas is used instead of a conductor. Ionized gas is used, right. It works as a conductor, but it is not visible. I mean, it is in a gaseous form. So, very high magnets, and through these magnets, high velocity of this ionized gas is passed, right. When it is passed, the EMF is generated. Now, this fluid, this working fluid may be a gas, or it may be liquid also. it is also possible to pass the liquid to have this effect. So, the temperature of the gas or the liquid is very high. So, MHD, what MHD does? MHD converts high temperature into the electricity. High temperature is attained by heating these gases. These gases are at very high temperature. Some separate arrangement is made for heating the gases. They are they go to the ionized form, and these ionized gases, when they pass through this magnet, EMF is generated across the ends of the gases, ends of the ends of the conductor. So, this MHD works on Faraday law of electromagnetic induction. Right. The system can use high temperature and high pressure gases also. Right. So, the MHD there are two types of MHD, open cycle and closed cycle. There are two types of MHDs. In open cycle MHD, there is a MHD, we can have an schematic diagram, there is an MHD, it has magnets, right. Just before MHD there is a nozzle. The function of the nozzle is, it is a convergent divergent nozzle, okay. The function of the nozzle is to provide the kinetic energy to the gases at the expense of pressure drop, right. So, there is a combustion chamber here, where combustion takes place, fuel comes from this side, hot air goes from this side, right. Fuel and hot air, they burn, high temperature gases are generated, high temperature gases are passed through this this magnetized field, and power is generated, and this gets the DC supply. DC supply is the output, and then it can be converted into the AC by a converter. Now, what happens to the gases which are coming here? Now, gases which are coming out, in order to save the energy, air can be preheated. Air can be preheated, it can be sent to the combustion chamber. So, that is how the energy can be utilized, but still after preheating air, a lot of energy remains, right. That substantial energy which is remaining can generate the steam generator. The steam generator is there, steam boiler, steam generator is there, where steam is generated. When the steam is generated, then further power can be generated. So, it is additional power we are getting from MHD. So, at the exit of the MHD, first of all air is preheated, remaining energy goes to the generator where steam is generated, and that steam is used for power generation. Seeding is done, some solid particles are mixed here, that is known as seeding, like potassium carbonate, potassium, sodium, they are mixed here in order to increase the efficiency of the system. Now, when the steam is generated, now here the seed recovery takes place here, again it is sent to the combustion chamber. Right. Now, these seeds they are again sent to the combustion chamber, or they can be mixed after the combustion chamber as well. There is no need to send them directly to the combustion chamber, and it is known as, and some seeds are lost in the process, right. So, some makeup arrangement can be made, makeup seeds. So, this is the general schematic arrangement of a MHD, open cycle of MHD. So, in open cycle MHD, you can use oil, coal, or any fuel you can use, and there is a small amount of alkaline material like cesium and potassium, they are used as a seed material. Normally, potassium carbonate is used as a seed material in such type of system. there is another arrangement which is known as a closed cycle. In the closed cycle, this hot air which is coming out from here directly goes to the chamber. It is a closed cycle. And during this course, of course, through a heat exchanger, heat is extracted to run the turbine. So, that is the arrangement of a, but the benefit of the closed cycle is it can operate on high pressures. It can operate on high pressures, right. So, the advantages of this type of system, first of all, it is reliable. It is reliable because there is no moving part. So, in those systems, any system which does not have any moving part is more reliable than a system which has a moving part. So, this is more reliable. Efficiency is also approximately 50%. If you look at the normal thermal energy to mechanical work system, the converts, for example, an IC engine, the efficiency is 33-35%, right. Turbine efficiency is also low. Overall efficiency, if you look at the thermal power plant, it is also very low. So, this efficiency is quite high efficiency. We get no pollution, or power is free from pollution, right. And the best thing is, the moment you switch it on, you get the full power. In other system, it takes time to come to the full power. Warming up time is there, but for this, warming time is minimum, right. So, the moment you switch on the system, you get the full power. It is smaller in size. And operation cost, because there are no moving parts. So, operation cost is also less in MHDs. It gives better utilization of fuel. And if you go for the high capacity production, the cost is comparable with the conventional power plant. The cost is also not very high, but it is still recommended for the peak power plant as not as a base power plant. There are certain disadvantages also, because when there are advantages, there are disadvantages also. Disadvantages is when there is a flow of electron in MHD, it is observed that this side becomes cooler and there is a reverse flow of electrons. Now, in order to overcome these losses, the L by D can be increased, or the length of the magnetic field is increased more than the required, that is one thing, or beyond the end of the MHD, it can be extended. Friction losses are very high because the fluid is moving with a very high velocity. So, energy losses in friction go up to 12 to 15%. So, they are the major disadvantage. Now, what happens? The gas is a very high temperature, right, and the trailing side of the electrode, their temperature is relatively low, because this side the temperature is relatively low. When the temperature is low, resistivity increases, and when the resistivity is increased, there is a large voltage drop in the trailing side of this MHD generator. There is a delta voltage drop is high. That is also a form of loss, energy loss. The next one is that we are using magnets of high capacity. The magnets are costly, they are expensive. So, magnets we are using here for MHD power generation, they are expensive. So, that also escalates the cost of the system. Now, third thing is when we burn the fuel here, there is a molten carbon ash, the ash is also comes into the molten form. So, there is a molten carbon in the gas, and the molten carbon sometimes it leads to the short circuit. So, this is also one of the disadvantage of this type of system. Now, we will come to the electrostatic. Mechanical generator. This device is not for a high level of power generation, it is simply if you have two containers, and it is simply conversion of potential energy water to the electricity, right. And the mechanism is very interesting, that water is coming from here, there are two vessels, positive, negative, positive it is neutral vessels, and there are two ponds. There is a cross connection to these ponds, right, and this is has positive charge and this is negative charge. Now, initially suppose this side is positively charged by, let us say, some by external means. When this side is positively charged, then this side will become negative charge, right. And when this become negative charge, it will repel the electrons in this direction. The electron will flow here, they will come here, right. When the electron come here, this side will become positive, this side will become negative. The water which is coming through these vessels, right, it will be collected in two different vessels down the line. One vessel has positive charge, another has negative charge. If you connect to this any charge measuring device or any let us say short circuit device, you can find a spark here. So, this is a very small scale experiment which depicts the the potential energy of water can also be converted into the electricity. Now, next is electro gas dynamic system. In electro gas dynamic system, there are two magnets and electrons are high velocity electrons are forced through these magnets, between these magnets. When high velocity electrons they are forced through these magnets, then EMF is generated. It is quite similar to the magnetohydrodynamic system, but in magnetohydrodynamic system they are ionized gases. Here it is only electrons which are moving in this, and they are on very high pressure and very high velocity, right. So, this is the working principle of this EGD, electrohydrodynamic generator. So, it works at a relatively low temperature. The benefit of this MHD works on relatively high pressure. Seeding is not required. There seeding is required to have efficient energy transfer. Self-contained. There is no need of steam generation in the system because it is a closed loop type of system. And you can continuously extract energy till the gas reaches the stack temperature. Continuously the energy can be extracted and the condensers and the cooling towers are not required. So, there are certain differences between EGD and MHD. The last one is nuclear batteries. The concept of nuclear batteries is that you take one shell and surround it by another shell, and this shell is kept at low temperature by circulating coolant, right. Now, in the center of this shell, if you put some radioactive material, the best suited is strontium 90. The half life of strontium 90 is 28 years, right. If you put it here, it will emit electrons, beta particles, and these electrons will make this surface negatively charged. Outer surface will become automatically positively charged, and you can extract energy from this. This is a very good concept of extracting energy from the nuclear power. That is not direct extraction of energy. Normally, extraction of energy of nuclear power is by utilizing heat of nuclear fission to the for converting water into the steam. But here, the fission is used the emission of the beta particle is used for charging these two spheres. When the spheres are, this sphere is charged negatively and this is positively, EMF will be generated. EMF for a normal size, the EMF it is of the order of 0.1 volt and it gives microwatts, right. But if the design improvement is done and further research is done in this area, we can also develop substantial power by this concept. Okay. So, this is also a sort of direct energy conversion. That is all for today. Thank you very much.